Volumes of other cross-sections, Part 1. Let R be a region in the xy plane such that R is the base of a three-dimensional solid. If we were to draw a representative cross-section, as we see right there, imagine that that is the base of a generally typical geometric shape that is coming out of the screen. We can see an example in the picture on the right side. There are, of course, an infinite number of these infinitesimally small cross-sections, where the volume of one cross-section is the area of the shape times the small width delta x. And to find the volume of the entire shape, which is above the region R, we would simply add the volumes of all those small cross-sections together. So in this video, I'm going to go over just a few basic shapes. You probably already know these, but these are the most common ones that get asked. Let's start with a square. So to find the volume of one cross-section, as stated above, it is the area of my shape times the width delta x. And the area of any squared is, of course, b squared, which makes the volume b squared, or base squared, times dx. So let's look above really quickly just to remind you what the base is. So over here, this is a representative cross-section, which could be a square, coming out of the page or out of the screen, where the area of the square is base times height, or base times base. The tiny width of dx gives it the volume. Another relatively common shape to be asked is a rectangle. Now, we all know that the volume of a rectangular prism is base times height times width. In general, the height is given. It could be something like the height is twice the base, or it could be something like the height is x. We will see specific examples in our next video. But let's continue with four more common shapes that you might see. So one shape you might be asked to find is when the cross-section is an isosceles right triangle whose base is a leg. Notice that if I take a square, which is drawn here, and I cut the square exactly in half with the diagonal, then you have an isosceles right triangle whose base is a leg. So if this is my base over here, and I have an isosceles right triangle that is coming out of the screen, where the base is the leg, then the volume would be exactly 1/2 the area of a square times dx. But what if the isosceles right triangle is such that the base is a hypotenuse of the isosceles right triangle? Well, notice that if you take a square and divide it into 4 equal parts by using the diagonals, you will make, right down here, an isosceles right triangle whose base is the hypotenuse. where the volume of this shape is exactly 1/4 of a square times the width dx. Now, for the equilateral triangle, I'm not going to go into a lot of details. I'm just going to draw a few things to help us see what's going on. But if I drop the altitude in my equilateral triangle, I make a 30, 60, 90 triangle. And then I know that the area is 1/2 the base times the height, which means the volume is 1/2 the base times the height times dx. But for an equilateral triangle, the height is √3/2 times the base. So the volume is √3/4 b squared times dx. Now let's look at the semicircle. One of the most common mistakes I see students make is that they say, well, the area of a semicircle is 1/2 pi r squared. Which is true, but we want the volume in terms of the base. And since the base is twice the radius, or the radius is half of the base, we see that the volume of a semicircle with a tiny width delta x is not pi over 2, but pi over 8 base squared dx. So in the next video, we're going to take regions that are the base of a three-dimensional solid, and we'll use various shapes that we've shown here to find the volume of our three-dimensional shape.